everybody. Welcome to the community conversation session. My name is Liz from Dfinity on the growth team. And if you're unfamiliar with the community conversation series, it's an opportunity to discuss upcoming contributions to the Internet Computer Roadmap, as well as other technical developments within the ecosystem. So today we have our very own Jordan Last of Sudograph here to give an overview and a demo. So please give him a warm welcome. Welcome, Jordan, to the Community Conversation series. It's so great to have you here.
Good to be here. Thank you.
Cool. So maybe you can tell us a little bit about your background, how you got into the Internet Computer. I think you had mentioned that there are some details around your Internet Computer journey that you hadn't previously made public. So I think we're all very curious to hear your story.
Awesome. Okay. Yeah. So just a few minutes before this call, I was just going through like, oh, what do I want to say? And I remember a conversation I had with a friend where we just discussed some things. I guess I've never really shared in a tweet or anything. I feel like they'd be useful, especially for people who are trying to understand the difference between the Internet Computer and other blockchains and other, I guess, similar projects with similar consensus mechanisms and similar goals. I think, especially if you're not a technical person, if you maybe haven't studied computer science deeply, it's very, very difficult sometimes to discern between all of the marketing of the different projects. The market caps are similar amongst many things, and the future is so uncertain. And so, yeah, just want to share some of those things. So first up, just background on who I am. Like, I grew up in this Silicon Valley area, so grew up in California. I assume that has a lot to do with my interests in life. My dad was a software engineer, so he was, when I was a kid, the coolest person ever. And he'd come back from work and I'd look to the window like, Dad's home. And he'd did little electronic projects with me. And I feel like that's probably what started my interest in computer science. And then I grew up in the 90s, so the web was just exploding as I was a kid. And just year after year, I guess new things would happen. I remember we were driving around Santa Clara one time and I saw Yahoo, the logo on a building, and I was like, holy, what? I thought some guy made that in his basement. It's like a thing. It's like a real thing. And so just over time, the internet, and especially the web, started to become a bigger and bigger, I guess, part of my life, but also, an interest that I had. And it was just fascinating, all of the amazing things that we were starting to be able to do. Just the idea, in 4th or 5th grade, I could enter a chat room and talk with anybody around the world was just mind-blowing to me. So I tried to tinker around with things. Probably lots of us are similar, right? You just get these interests and hobbies. And so, yeah, that happened, and just played around with, digital cameras coming out, all that stuff. So fast forward to going to college. I started my degree in 2009, and computer science was kind of the obvious choice. I actually started with computer engineering and then switched a year or two into computer science. And yeah, just tried to dive deep into definitely internet programming, very focused on, I guess, web development and such, but also more base layer internet protocol stuff. So understanding how the HTTP protocol actually works, how TCP actually works, how IP actually works. They would have us, walk through, and we do implement simple versions of that and such. So all that was going on. And for some reason, I started my degree in 2009. I took a little break to do some, I guess, service for my church as a missionary. So that took a couple of years, but I got back from that in 2012. And for some reason, even though I was fascinated with technology and I loved all this stuff, I had never heard of Bitcoin or any of that. So completely missed that until basically 2017. So that was when I was basically finishing up my studies in computer science. And so I don't know how it happened, but I guess I had heard the word Bitcoin enough times, and it was a little bit before the huge bull market. So it was around May 2017. I decided it's time to finally figure out what all this stuff actually is. And so the way that I learn things is, I get this little itch in my brain, and I just read everything I could find. I guess basically I download every podcast that has ever existed about that subject and try to consume it. And so that's what I did, starting with Bitcoin, I believe. Very quickly that led to Ethereum. And very quickly that led me to realize that there's this entirely new technology, as I put it now, a new computer that was being created. So Bitcoin was the first really decentralized computer that actually worked. That was, had the properties that you'd want from a decentralized computer, mainly, I guess, being security, and depends on how you define security. So yeah, just started consuming tons of things. Ethereum led me to other decentralized protocols, IPFS being one of those. And just everything from there, especially in 2017, 2018, 2019, we had an explosion of new projects trying to compete with Ethereum, trying to become, I guess, the Ethereum 2.0. And even though I'd been spending a good chunk of my life at that point studying technology, experiencing, an information technology going from, I entered in the 90s, the internet started multiple decades before that, but the web at least really came about early 90s and just kind of exploded, going from, a few people to millions, and today billions of people. And so I felt that this was something similar. Like, I felt that there's something very, very important here, very powerful here. I think part of what drew me to the web and the internet was its amazing potential to basically do good and to expand, the capabilities of humans, right? I like to say, like, a new, what's that word? Whatever. A new capability for mankind is unlocked. Anyway, so yeah, Ethereum, all the competitors all exploding. It was still confusing to understand, like, well, what's the difference between all these? Most of them are open source. Big difference between that and the early web days. A lot of the competing web type protocols were closed source. So, but this is different. It wasn't multiple companies necessarily trying to come in and just create a proprietary empire. These were actually a bunch of open source protocols, all trying to essentially do the same thing as well, which is become basically a world computer, or at least, a decentralized computer that is permissionless, that is open source, that is credibly neutral. And we had tons of these. So, for example, Cardano, Near, Avalanche, Algorand, Zilliqa. There's all kinds of these. Solana, Binance Smart Chain. Some came around later than others. So basically 2017 was just kind of learning stuff. 2018, I think, is when I started to kind of solidify by, diving deeper into actually reading like the Bitcoin white paper and such. But it became clear that I needed to, I didn't want to just waste my time. You just can't be a part of every community. And so I wanted to really, for financial reasons, obviously, and also like for my career and for just being able to use my skills as a software engineer or developer on the thing that's, I guess, going to pay off the most for myself and for others. I didn't want to spread myself too thin. So I started to really study and try to understand the difference between all these. And I guess what I wanted to share was, like, I found the internet computer just a few months after I found Ethereum. So I think it was about October 2017. I just found the website, and the vision seemed pretty excellent, but many visions seem excellent on a website. And so I went to the handy dandy podcast app and searched Dfinity or Dominic Williams. And there actually were a handful, like maybe 4 or 5 podcasts, even from years previous. I think 2015 or 2016 might be the first that he had ever spoken about it. And just instantly hooked by Dominic's vision and his understanding of these protocols and just how it works. Just how technology consolidates, how there's going to be basically one world computer, and how Like it's that world computer vision that is so powerful. I mean, it just really resonated, and that he was focused on scalable virtual machines. I felt like he was very able to boil it down very well. And so that became, I mean, I guess an obsession of mine as well. It's like, which one of these decentralized computers or virtual machines is going to be the scalable one? And basically I went to like every crypto conference I could find on the East Coast, at least. Luckily I had family in San Francisco area, so I could just head home anytime and just, stay for free there. And basically over 2018 and 2019 for the pandemic, I met with as many blockchain projects as I could, just going to all the meetups, going to the main events, East San Francisco Blockchain Week, etc. Dominic Williams was at multiple of these things. I was actually able to find him and talk to him in person, interrogate him about, all the things that he's saying that are possible, but that I didn't understand how they could be possible, right? Like, how is it possible that you can do these things when no other project can do them? Also, 2019, I was able to talk to Charles Hoskinson of Cardano. This was during the dark years of Dfinity. That, there was a period where it just kind of went dark, and they were heads down and dealing with their own problems. So I was able to find Charles Hoskinson in Wyoming somehow at a conference, not just like on the range, but interrogate him too. Like, what's the difference between you and Dfinity? What is going on here? Blah, blah, blah. He told me his spiel. They were hiring similar people. They had similar visions. Still left me confused, but I was at least able to try to get the lay of the land. Talk to the team at Near. Near is, working on a sharded blockchain. Same goals basically as the internet computer. Also able to talk to core Ethereum people working on the vision for sharding. I was really trying to understand, who's working on sharding, how's the sharding actually going to work. And I found in almost every instance, also the Harmony team, was able to kind of talk with them. And I found out very quickly that Ethereum's vision was to basically have capped sharding. Now, over time, they're going to, lift the cap, but it was very obvious that they weren't going for an infinitely scalable blockchain. Even back in like 2018, 2019, it was obvious that just wasn't the design. And they still haven't figured out sharding. Like, that's not even, it's like kind of out there on what they're going to be able to achieve. Near claimed that they had an infinite sharding. Harmony, I think, claimed that as well. It was pretty obvious Harmony was just kind of starting out with things. And so that didn't seem all that promising. I also, at that same time, was coming up with the idea that would eventually become Sudograph. Basically, the idea that, imagine if you had a GraphQL database that was infinitely scalable, secure by default, always available. All you do is write the schema, which is just, the types, the application-specific data types or data structures for your application, and just hit deploy. Everything, like, ideally the vision is that should be extremely simple to do, right? You should just be able to think at a high level, what does the data look like, and what are the relationships between the data, and all the crazy scaling and all of the, like on AWS, the things you have to deal with are crazy. You have to deal with security groups locking down your IP ports, making sure your operating system's up to date, having read replicas possibly on your database, dealing, if your database is running out of compute capacity, scaling it up possibly, dealing with backups, dealing with your own virtual private clouds, setting up, CIDR blocks with basically subnetworks, and it's all this crazy stuff. It's absolutely fun. It's insane. Dominic is correct when he says it's a Rube Goldberg machine. Like, that is what the legacy traditional IT stack is. I just spent like 2.5 years at a Web2 company before what I'm doing now, just dealing with all this craziness. Like, and before at like previous startup, the same thing. How are we going to scale stuff? How's this actually going to work? Jumping from, back end as a service type stuff, that broke down. Jumping to my own infrastructure, just always trying to use GraphQL, it just always broke down. It was always inelegant and unideal. And so hopefully this all is a little bit coherent, but that kind of GraphQL vision coincided very well with the internet computer vision. And so the internet computer was not live back in these days, 2018-ish, 2019. So I took that GraphQL vision to the Ethereum Foundation. And I laid out basically what Sudograph is. It's, I called it like Graph DC, decentralized GraphQL at the time. And I said, listen, you should be able to author smart contracts with GraphQL. It'd be so much simpler. Like, just define your data type and hit deploy. Took it to them, talked to them. Hopefully it's obvious why that didn't work out. If you're not aware, Ethereum is an incredibly limited environment. The resources are so constrained. That's why it's so expensive to do anything. Now, it's extremely secure, and that's what's amazing about it. It's secure, it's incredibly neutral, but it's like a very puny, tiny computer, in capability. Not in capability, it can compute anything that's computable, more or less. It's virtually turn complete. But how long it takes and how much it costs to run those computations on Ethereum, it's just incredibly expensive, and therefore it's extremely limiting. Therefore, you can't take a GraphQL implementation and deploy it into a smart contract environment and expect it to perform at all. So, needless to say, I did not get funding from them to do that, and that's good because it would have turned into nothing. So, just kind of kept with that, just kept going the lay of the land, trying to figure out which project is correct. And in my opinion, the internet, protocol level things such as the IP protocol, TCP protocol, these things tend to consolidate. You don't have 20 different IP protocols trying to run all the communication of the world. You have one. And sure, there's IPv4, IPv6, but IPv6 is a successor. And I believe it's going to be the same with the internet computer or other decentralized computers. Basically, we're going to consolidate to one or a few players. And so it wasn't until this year, basically, that I've been able to basically get all the information I needed, get the math. The Chanky paper is absolutely out of control. I don't understand almost anything in there. The internet computer consensus paper, I understand much more of, and it makes a lot more sense to me. It's very easy to compare that to other consensus protocols of other blockchains. And actually the last week or so, I've been, I guess taking some time off to really dive deep into the consensus layers of the internet computer and other protocols as well. And, Solana, grab the white paper, read it, their proof of history, proof of work combination kind of Cardano. They come up with their own thing, or Ouroboros, it's a proof of stake thing, blah, blah, blah. Tendermint is a PBFT type variant, which is very similar to internet computer consensus protocol. The point is, most projects, the internet computer they're just not going to be able to compete with it. Like, Ouroboros has a theoretical or a practical limit of like 200 transactions per second. Just go look at the white paper. And it might even be less. And that practical limit was testing on AWS. Solana has a theoretical limit of like 700,000 transactions per second. Ethereum probably will max out in the millions or low million, in the next few years, maybe hundreds of thousands. Maybe they can push it over time into the millions. The internet computer is the only protocol that I see that can credibly have unbounded capacity. So I just wanted to share some of those things. Like, I've really, really, really tried to, I guess, run the gamut, interrogate teams of major protocols. Obviously, you haven't talked to everybody. Studied not all their white papers, but some of them, and definitely haven't read, even of those, haven't necessarily read all of them in detail. But that's kind of my journey here to where I am with the internet computer. It is a new computer. Like Bitcoin started, it's a decentralized computer. Ethereum is, I would say, that definitely the successor to that idea of a decentralized blockchain computer. And everyone's trying to be the successor to Ethereum. And the only one, in my opinion, that really has a shot is possibly the internet computer. And you can listen to, I've talked about this on my podcast, Emergence. It's not a done deal. that the internet computer will somehow overtake Ethereum, or that Ethereum will overtake the internet computer, or that they'll work together. I think the jury is still out on those things, but the internet computer is the only decentralized computer that I think has a chance at being orders of magnitude better in some key way over Ethereum. And so that's part of why it's so promising and exciting to work with. And so that's how I got here. And that's how, I guess, how Sudograph, the idea, came about as well. So that's about it.
Jordan, that was I have to say, like, for me and also for the people in the chat as well, I felt like the passion for the vision of the internet computer was just like reignited listening to your journey. And I think it's really great that in a space that's so full of people that I think don't take the time to do their own research, that you've clearly done a deep dive and your analysis is really based on your experience and data and so on and so forth. So one quick thing, Jordan, I think your microphone just switched. So it is sounding a little bit soft. It just happened. So for almost all of the, almost all of what you had just spoken, it was totally fine, but just wanted to give you a heads up because some people in the chat are.
Yeah, let me reset
Okay,
that.
perfect.
Okay, is it better?
That's much, much better. So yeah, love to see your passion for the space. You are one of the invaluable contributors to the internet computer ecosystem, I would say. So do you want to give an overview of Sudograph and run through a quick demo for the crowd here?
Yeah, let me just share my screen and just jump right into that. So, all right, so here we go with Sudograph. Okay. Okay, Sudograph is a GraphQL database for the internet computer. The whole purpose, as I explained earlier, is to take a schema. Let me show you what a schema looks like. I keep sharing this example. Hopefully it's not too boring. This is what a GraphQL schema looks like. It's a very, very simple, I mean, even if you're not a software developer or engineer or anything, you could decipher this if you spend a little time, right? Basically, you're defining the types. If you have an Excel spreadsheet, for example, the columns might be these types, right? If you have a Postgres or MySQL database, the table would be one of these types. A MongoDB document would be one of these types, right? You have a type, it's just some data you're going to store, and then the type has its own fields. And each field has its own type. And that type can be a scalar, like a primary key, or a string, or a date, or it can actually be another type. For example, this user has an array of blog posts, and this creates a one-to-many relationship. And you can see, hopefully, that with a few primitive data types and with the ability to link to other, these are called object types in GraphQL, you can basically create arbitrarily complex data types. And GraphQL is awesome because it does let you think at this high level. If you have a whole team of backend engineers that can take the schema and go implement it. So there's a ton of work that still goes into actually using GraphQL in practice. There's basically, you implement GraphQL with something called resolvers, and resolvers are functions that will take GraphQL queries and go to a database, go to a file system. What's amazing is it can go to any arbitrary data source and it can retrieve that data for you, but it doesn't do it for you automatically. And so that's what makes GraphQL still difficult to deal with. So hopefully you agree. In an ideal world, maybe it's not practical to do it, right? We'll see. But in an ideal world, if you just wrote something like this, and if it generated the entire database for you, right? And it was performant, and it could, scale to any load, and if it was secure or allowed you to, put in authorization and such, that is getting close to a perfect solution. At least we as humans, what might be perfect. Look how declarative this is. It's like I could just speak this to you. I have a user. The user has an ID. The user has a username. The type is string. The user has blog posts. It's declarative. You're describing what instead of how. And that's really the magic here. That's the key. That's the whole goal, is just to make an entire database, just generate it for you automatically with everything you need, all batteries included, migrations, indexing, authorization, everything. And also in the future, subnet types, right? Like you can imagine, let me jump over here so I can type this. You can imagine in the future, I might say something like, or let's see, type user should be deployed to a subnet that is, replicas that has 7 replicas, for example, or 30 or 100. And maybe it should be a private one too, so that it actually uses secure enclaves and everything. And obviously this will be probably a lot more expensive than a non-private subnet that only has like 10 replicas. The whole point is that you should be able to configure everything with a very, very simple language and a universal standard language, which GraphQL is quickly becoming, in my opinion. You shouldn't have to write crazy Motoko or Rust to configure all this stuff. It should be very simple. And so that's just a high-level overview of the whole point and purpose of Sudograph. And so I guess I'll dive into how you actually use it. So here's a basic project. By the way, this is the Sudograph repository, right? You can see the URL up here, hopefully. And in the examples, so here's the main repo. If you go to examples, I have a bunch of examples doing various things. Here's the basic example. Basically, this basic example has 3 canisters, a front end, a playground, and a GraphQL canister. The front end is going to be, like, imagine this were your project. This is just the application specific thing. It could be whatever you want. In my case, it's just a website. The playground is something you probably are going to want to do if you're using Sudograph. It is, shoot, I can't click. Here you go. It's this. It's a GraphQL playground. It gives you, let me move this thing. It gives you documentation on all the queries you can do, all the mutations you can do. You can look at the types and get information about everything. So it just documents everything that's possible basically and lets you actually execute queries just right here. And this query is actually executing directly against my local replica. And this works locally or in production. So, I should show you a production one too, but I'd have to look up the canister ID. Okay, and finally, this is the real core of it, is the GraphQL canister. You can call it whatever you want, but basically it's a Rust canister that is actually going to house your database. So it's this Rust canister that takes your schema and generates everything for you, all the Rust data structures, everything. And you can execute queries by calling into that canister from a front end, from an iOS app, an Android app, from a server, from another canister. So that's what allows you to integrate with Motoko if you want, right? You could just have a Motoko canister that does a CrossCanister call into Sudograph. Maybe in the future, Sudograph will be able to be deployed with Motoko all in one binary, but for now, you have to do a CrossCanister call, which hopefully isn't too bad, especially within the same subnet. So that's just the canister architecture. And there's nothing crazy up here. This is just some basic configuration stuff, cargo.toml for Rust, nothing crazy. A very simple package.json. So let's jump into the GraphQL canister itself. Here's where your application-specific cargo.toml will be. Basically, you just say it's a library. And you don't even need line 12 anymore. You just include Sudograph. You don't need this crazy thing. That's just for me developing locally. Just say Sudograph, pass the version in, create a schema like I showed you before, and then create your you create your Rust file. This is a very simple example. It doesn't have authorization or any kind of custom resolvers or anything. It's just the basic CRUD of a database. And so this is all you need. You just import the GraphQL database procedural macro, and you call it by passing in the path to your schema, and that's it. Like, this will generate an entire database for you. So, and like I said, it doesn't have authorization or crazy custom stuff, but hopefully you'll see very soon that it's incredibly able. It's lots of utility already. And then you'll have a did file. So by default, Sudograph will generate a GraphQL query and a GraphQL mutation function on your canister that is exposed to the outside world. And that's it. This is the implementation of the canister. So let me try to get to this playground again. So yeah, this schema that you saw here, let me show you everything that you can do with it. So basically, we have two types. And so we have these read queries. You can read a user or read a blog post. Let me skip search for now, but you have limit, offset, order. You can order by any scalar field, one field at a time. And limit, offset, and order combined gives you paging capabilities. So like, give me only 10 records. When they hit next, load the next 10, something like that. And then the search here is extremely powerful. The search allows you to do very complex querying. So for example, I might want to search for all users where they're created at equals a certain date, or is greater than a certain date, or greater than or equal to, or less than or equal to a certain date. So these are all of the operations you have for date types. And then string types have even more. We actually have contains, starts with, ends with, and these can go on and on. They're not that hard to add depending on what you want to do. And then what's really cool here is that we have cross-relational filters as well. So you can actually search by users and search by those users' blog posts. And this is recursive. And so I have all the search capabilities of the blog posts available right there. And you can also do arbitrary ands and arbitrary ors. So that's cool there. And then mutations, just CRUD. I can create a user, pass in my fields. I can create a blog post. I can update user, update a blog post, delete a user, delete a blog post. And initialization, you usually don't have to do that, but that just basically initializes the database. Pseudograph does that for you automatically, but it is exposed to you so that you can use it if you need to in other contexts. So hopefully you can see that the CRUD is just entirely generated for you. And now let's actually use this thing. So yeah, there are no users in my database. So my read user query right here just returns nothing. But let's create a user. So if I want to create a user, I use the create user mutation and pass in this input object. I'll say username is last.mjs, and I'll execute that against the replica. And there you go. I have a user, and it's generated an ID for me automatically. And let's go back to this query. There it is. What's amazing about GraphQL is I can ask for exactly what I want. So if I want the username, I can put it in. If I don't, I leave it out. And it's just super awesome, right? So there's that. Now, let me make a blog post. A blog post, if you noticed, requires an author because of this exclamation mark. So it cannot be null. Luckily, I just created an author, last.mjs. So I'll grab its ID, and I'll create a blog post here. And notice I pass the title in, and then I connect myself as the author. So this creates the relation in the database. And I'm going to just ask for all these fields. Give me the title, give me the author that I created, and its username, and its blog posts, and its ID, and its title. So actually, that was a little too confusing. Let me just comment that out. We'll just start with asking for the ID and the title. Okay, I created a blog post. There's the ID, there's the title. I can ask for the author, which should be last.mjs, right? Oh, shoot, I always do that. I just created 2 blog posts. Let's read the blog post. Here we go. Hold on. Okay, I now have 2 blog posts. They're both named blog post 1. And now I'll ask for the author and ask for the author's username, and they should both be last.mjs, and they are. And here's what's cool. I'll ask for that author's blog post, and they are both blog post 1. And I'll ask for that author's blog post author, and it should be last.mjs. It just keeps going on and on. Wait, sorry, username. There you go. So you can create these arbitrary complex queries, which is nice. And then I'll show you the search capability real quick. So Okay, give me all the users. Let me just simplify that for you. Okay, give me all users. There's only one. So I can say something like, where the username contains M, I'm going to show up. Where the username contains Z, I'm not going to show up. Where the username starts with L, I'll show up. Starts with X, I will not show up. Starts with last name JS, I'll show up. You get the picture, hopefully. And then I'll do a cross-relational one. Give me all the users where the blog post title equals blog post 2. There are no users with the title where it equals blog post 2, but blog post 1 does work. And we should be able to verify that by adding the blog posts in. Yep, there they are. And we saw all the capabilities over in the documentation over here. So you have all those available to you. And let me just update one of these blog posts for you. Update blog post. I'll change this blog post to say blog post 2. Nice, and we can verify that up here. Notice that my last MJS user now has a blog post that's blog post 2. And then what I can do is, why don't I just delete that blog post? Sure. Okay, those are all the blog posts. You can see them. And now we're going to delete one of them. Just pass the ID in. Okay, should be deleted. Now, if we go read all the blog posts, they're showing me 1. Yep, so blog post 2 was deleted. And that's it. So, I mean, that's the basic demo. You make schema and you do all this stuff with it. So I'd love to answer questions if there are any. Otherwise, yeah, I guess we'll see what questions are.
Oh, no, there definitely has. Okay, first of all, people are like reeling because they are just loving your story and they love everything that you've shown us. So we do have around 15 questions in the Q&A. So I will try to get through all of them. So the first question is, would you consider Sudograph the first middleware for the internet computer ecosystem?
I mean, depends on what you mean by what middleware, but I guess I don't know what you mean by middleware exactly. Like, there's Express middleware. In that server context, there's, yeah. So if you mean by middleware, I don't know, it sits between the user and the implementation of your database. Yeah, it's a middleware. And what's cool about the implementation of Sudograph is that the GraphQL layer is separate from the database layer underneath. So in that way, you could definitely, I think you could think of it as a middleware layer. And that database layer can actually be swapped out. So I made my own relational database called SudoDB. But imagine, let's say someone compiles SQLite and it's actually amazing. I could swap SQLite in if I wanted to, or some native graph database, swap that in, whatever. So yeah, possibly.
Cool, thanks, Jordan. So there's a community member who could not make this talk, but emailed me a question. So their question is, what is the current query methodology across large data sets? What kind of performance are you getting? Are you using hash maps or some other kind of structure to speed up the queries?
Okay, right now, Sudograph is in beta. So I actually haven't focused on optimization at all, really. What I focused on is just getting it to work. So you've noticed that it does work. I did not pre-record this. You should be able to download this and do this yourself. But it does break down in performance as you add. I don't even know, but even with maybe thousands might be okay, but tens of thousands, hundreds of thousands of records, it breaks down. I made an Ethereum archival canister prototype. I pumped in like around 2 million records, and because I don't have indexing implemented, basically I ran into cycle limits. So, and it took like 5 or 10 seconds to do queries that with indexing, I'm hoping would take hopefully far less than a second. So optimization is not there right now, but the plans for optimization are basically to put in indexing. And I'll just talk real quick about, you asked about hash maps and such. So I'm using B-tree maps right now. Basically, I just compose multiple B-tree maps together to create the solution. The Internet Computer has allowed me to shed a lot of the complexity of a relational database and just get down to the core data structures. And so basically, if the consensus on relational databases seems from my research so far to be to use a combination of B-tree or B plus maps and combine that with binary searches to get the theoretical maximum search speed. So I plan to do that. I don't see any major reasons why that won't work. The biggest issue is going to be scaling outside of a single canister. The canister limit is about to be lifted over time to hopefully 300 gigabytes. And that should be lifted eventually, I think, into terabytes. So that's going to really help. But basically, mutations will still be a problem for a while. We need to figure out how to scale update calls, because update calls are limited to basically the capacity of a single thread on a single machine. So reading and querying, I think we will be able to scale that infinitely easily. The protocol hopefully will add read replicas to subnets that are at capacity, and a GraphQL database could easily be copied, and those queries should be able to execute very quickly with indexing. It's the mutations and the update calls basically that will be the most interesting on scaling. But I think many applications, especially as they start off, are going to do just fine with 300 gigabytes of space and the update capacity of a single subnet, which I think you could push with Sudograph into the possibly thousands of mutations per second, because you can group many mutations into one GraphQL mutation and just send that all in one update call. And Pseudograph should just crunch through those really fast. So hopefully that answered most of the question.
No, it's very thorough. Thank you, Jordan. So next question is an interesting one. Are there any canister use cases that you would not recommend a Pseudograph for? For example, do you think it's overkill for basic CRUD canisters?
If your CRUD canister, if it's actually a basic CRUD canister where it's like extremely basic, like save a value and retrieve it, then I wouldn't use Pseudograph. If you have any type of non-trivial querying, like all the stuff I showed you, where you have relations, one-to-one relations, one-to-many relations, many-to-many relations, and you might want to have complex searches across, even simple searches across, you're going to have to implement all this stuff yourself. So unless someone else has a CRUD solution as well that does this, I have not seen any that has this capability. So I would say, here's what I imagine. I imagine most developers in the future reaching for Sudograph or something similar. Like GraphQL is, in my opinion, like the end-all be-all solution for a majority of CRUD applications. Obviously, when you get into the particulars of certain things break down. But I would really reach for something like this. Basically reach for this. But what you want to be careful with at this point in time is the fact that Sudograph is in beta and it's so early. So if you want to move very, very quickly and have surety, basically, that you can overcome any solution on your own timeline, you should probably, I guess, implement application-specific stuff for yourself. But if you're prototyping and you're not maybe raising a ton of money to start some project that has to have tons of users in the next few months, honestly, I would reach for this first. And I plan to have a 1.0 by the end of the year, definitely addressing optimization, addressing things like migrations, and addressing authorization. So this is going to be a excellent solution, at least by the end of the year, or at the latest by the end of the year, hopefully. And there are multiple, a handful of projects that are using it right now. So hopefully that makes, and just reach out to me if you want more details. Just DM me or whatever, we can do a video call.
Cool, thanks, Jordan. And even in beta mode, I would say it's already had a big impact on the internet computer ecosystem. So excited to see what future versions have to bring. So next question from the Q&A: what sort of security does data stored in a Sudograph have from the node providers running the canister?
So Sudograph is no different than there's no difference between data stored in Sudograph or data stored in any other canister. So first, I just want to say that. Next, you'd have to probably talk to the Dfinity team to really understand the actual security mechanisms that apply to the node operators. But my understanding right now is that everything's in plain text. The node operators do have access to the machines. So technically speaking, there might be some things to hinder them, but technically speaking, I don't think it'd be that difficult for them to read the memory of the canisters. So it's in plain text for the node operators to see. You should just, that should be your default view of it. And by the way, a lot of these questions go to my podcast, Demergence. I do like sometimes full episodes discussing these issues. So privacy, I think I might have done a full episode on privacy. So just assume that the node operators can see the data. That's just privacy. For security, as in, making sure that no one can change it, that goes down to the consensus mechanisms, the Byzantine fault tolerance of the internet computer itself. So as long as you have less than a third of the node operators that are, Byzantine are able to collude, your data's or your canister will progress. And basically, as far as I understand it, the subnet's going to shut down if the BFT properties fail. So it would be extremely difficult for the data to be corrupted. Now, they want to implement secure enclaves to help hide the data from the node operators. That would hopefully help, but side channel attacks like these secure enclaves are not a perfect solution, and they may never be a perfect solution. We might need better technologies like fully homomorphic encryption or performant multi-party computation to actually get, I guess Byzantine fault tolerant privacy, which is not something I've that's a concept that I haven't thought too much about yet, but you just got to be careful. It's not like AWS fully, and it's not like Ethereum fully. Ethereum's fully public. AWS is fully private with one overlord that can just look at any time. The internet computer is kind of like, not fully public, but it has as many overlords as the subnet at a time. So, yep.
Hey, Jordan, sorry to interrupt, but your volume is a little bit soft again, just as an FYI.
Okay,
yeah, that's great. Cool. Thank you, Jordan. So next question, what does a reverse lookup look like in Sudograph, Jordan?
What do you mean by a reverse lookup?
Perhaps the asker of the question can clarify in the chat. So while they're clarifying, can move on to the next question. So next question from the community: does my business logic go into a separate canister as part of the Sudograph canister, or as part of the Sudograph canister?
You can do it either way. So you could take your business logic and just add it. So I can just show you, right? I mean, this Rust file is what's deployed. So just below here, just start typing your business logic out. You can do that. Or you can put it into a separate canister and just do CrossCanister calls. So either way.
Great, thanks, Jordan. Next question: are there any benchmarks performed to see how the database performs on hundreds of megabytes or gigabytes of data, especially aggregation queries?
Yeah, so for now, I would be limited to 4 gigabytes anyways in any of those tests. And basically my tentative roadmap for September is indexing, and that's when I'll be creating the benchmarks to answer those questions. The answer right now is it would break down and you would be sad.
Hopefully that would be changing soon with more canister storage. So next question: how does the database store the data under the covers? Is it inside a key value store?
Yeah, it's just well, let me show you actually. So it uses the internet computer's orthogonal persistence. So basically I use native Rust data structures to actually store the data. And if I go to sudo db, here's the database. It's very simple. By the way, a lot of this needs to be refactored, but here is the beginning of that. So this B-tree map is a standard collections B-tree map. And basically I map each object type name to an object type. The object type is a struct that has the object type name, has a field type store, which is another B-tree map, and a field value store. The field type store has typing information about every field. So every field here's the B tree map has a field name and then a field type. So that gives you typing information, which is good to help, necessary for multiple reasons. And then the field values store down here is a B tree map that maps the actual primary keys to the actual field values. And I guess the field value is another B tree map that has a field name and the field value. So I can pose basically multiple B tree maps together just to get the basic structure. And indexing should be able to, I'm thinking it'll work just like this. I'll basically add a index store, which is very similar to the type or the value store. And that indexing is going to help me when I'm executing queries to perform binary searches, essentially. So that is how that works.
Cool, thank you, Jordan. And we got a comment from the chat saying this approach is so simple and clean, wow. So next question, how does authentication work with Sudograph? Does this integrate with the internet identity?
Yeah, let me show you that. So yes, it does integrate with the internet identity because they did an amazing job with the internet identity and made it extremely flexible. So basically on the front end, you could just use internet identity. Let's see if I can give you a quick example of that. Here we go, authorization. Oh, I don't have an example for authorization. I will show you an example. Let's see, files has it. Yeah, okay, so here's like a basic file application. And yeah, so notice this is the front end. So here's an identity from @Dfinity agent. And down here, I authenticate. This is just a basic way that, just follow the documentation to figure out how to authenticate. But basically, once I get an identity, I store my identity in my state up here. And then when I initialize Sudograph on the front end, I pass the identity in right here. Because this is asynchronous, this is not as straightforward as it could be. But this Sudograph object has a query and a mutation function on it. I can show you a better example of the front end without the asynchronicity. Normally, you can just do this. So on the front end, you just pass in a canister ID, get the query and the mutation. And right here, basically, you can pass an identity in. So you just need to obtain an identity and pass it into the client, and then you'll be able to authenticate. And so the backend looks like, in this case, you would make a custom GraphQL mutation. And this is just hard coded. I just check the callers principal ID. Oh, no. That's canister. Sorry, right here. I check the caller's principal ID against my hard-coded last name JS principal. This worked for my app because I knew that on the front end, I only wanted to allow this, this principal. And so I just panicked. But basically, what you would need to do for now is make custom functions that implement the authorization. And then after that, you would execute your GraphQL mutation. In this case, I'm using the generated GraphQL mutation. But in your case, you might have to create a custom function that would execute the GraphQL mutation within the canister, essentially. Hopefully that made sense. But basically, the front end, you just use internet identity or other authentication means. And then on the back end, you can create custom functions to handle authorization. And by the way, to make this secure, you need to turn off exposing the generated GraphQL mutation. And so there's actually a special type called Sudograph settings that will have all these crazy settings for you that you can turn on and off. And there's more settings than this, and there will be more coming. And so it's just another example of how it's very declarative and simple.
Great, thank you, Jordan. Next question, any plans for a code-first approach instead of a schema-first approach, like accepting schema generated by Nexus.js?
You could definitely do a code-first approach if you want. Right now, I think you just go in this file, and I use async graph. Let's see, GitHub. Async GraphQL is the GraphQL library that I'm using. And so you basically have full access to this library from within a Sudograph canister. So I haven't tried to really do it. So there might be little issues with like name conflicts or something. But theoretically, if you don't want the schema, just ignore it and do everything with async GraphQL.
Great, thank you, Jordan. Next question, what does the CrossCanister call for Motoko look like to run a query?
Yeah, let me see. I should have an example of that. So Motoko client, here we go. So here's a Motoko canister. It looks like this. So here's a function, get all users. And basically I created my GraphQL canister. Actor, here's the canister ID, and it has these two functions on it. And then you just call it and you pass in your query as a string. So it would come back as text. So it would be a JSON string. And so from there, you would somehow need to serialize it into your data type. I haven't worked much on that. So hopefully it's pretty easy, but you might be able to define some candid that would have the structure that you want. But at least you get the text back and it's JSON. So good luck with that, I guess.
Cool. Thank you, Jordan. So the next one might be related to what you had said about adding indexing down the line. But the question is, does Sudograph support secondary indices to optimize queries?
I'll address that. Secondary as in not generated. Oh, I guess I can't ask you and you can't answer me. So I'll just say what I'm assuming. So
yeah.
I think if you mean by a primary index, the index that's automatically generated by the database. If that's what you mean by primary index, then a secondary index would be, defined by the developer. I'm going to start with primary indexes first, and then I guess I'll see from there. Like, I don't know if in September I will promise primary or secondary indexes, developer defined indexes, but it's obvious that you would need that. So I don't see why it wouldn't come in the future.
Great, thank you, Jordan. So we are nearing the end of the questions. I see two more. So is all Sudograph data auto-magically persisted in stable memory?
Oh, no, it's not. So it's not. So yeah, every time you deploy, if you don't use it, put it in stable memory and then copy it back, it will be destroyed. That's what October, I believe, is what I'll be focusing on, is migrations, which will do that automatically for you. But let me show you how you migrate right here. Oh, I don't have a migrations example. It's probably in the documentation. So if I go to the Sudograph book, then I think there's a migration section down here. And I feel like I did this somewhere. It might be in the Ethereum archival canister. Yeah, here you go. So you just need to hook into the pre-upgrade, use the pre-upgrade macro and the post-upgrade macro. And in pre-upgrade, you basically copy the object store. Remember that data, that data structure, that B-tree map that I showed you? It's all self-contained, the entire database in one B-tree map. And so you just copy that into stable memory, and then in the post upgrade, you just pull it out. And it's a little bit complicated, but you just go through each key and value and you insert it back. So that's what you have to do for now.
Okay, wow. And we're getting some comments in the chat around how thorough your documentation is. Did you write all of that, Jordan?
I did.
Wow, we should take some pointers from you. It looks amazing. So we are rounding up on time. There is one final question. So it is, wouldn't CrossCanister queries be absolutely essential for business logic canisters to be able to quickly query Sudograph canister data? Right now, CrossCanister queries are not supported.
CrossCanister query. Oh, CrossCanister queries. Yeah, absolutely. Actually, in Rust, you can do CrossCanister queries, I believe. So if you use Rust, you're fine. But yeah, that's true. And I think they're working on it. So go check the forum and look at the roadmap. I think it's obvious that they want to fix that. I think I might have even talked to them about that. And it was a concern, but not a concern anymore because I think they will address it.
Cool. Thank you so much, Jordan. We are at time. I will send you the chat transcript because people just absolutely loved your talk. They loved this demo. We're really, really keen to see what will come with the roadmap for Sudograph in the months to come. and looking forward to tuning into the next community conversations with you guys. Cool. See you later,
Sweet.
Jordan.
Thanks,
Bye,
guys.
everyone. Take care.